I couldn't get over the idea that you could see photosynthesis, you could graph it, and then many years later I would have explained to me by Jason why that's not photosynthesis.
Hello and welcome back to Leaf, a LI-COR plant physiology podcast, which is, of course, based on The Hitchhiker's Guide to Leaf-Level Gas Exchange, a book written by Jason Hupp and Dr. Richard Vath. This is episode 8, which means that we have left thinking like a plant, and we are now in the last section of the book, looking deeper. This episode is all about integrating fluorometry with leaf-level gas exchange, as the chapter implies, and this audio may sound a little worse than I normally have it. That's because I'm very excited to have a new guest on today who is joining me from across the pond, so please understand that this is via Teams call, and the audio may be a little bit rougher, but I'll go ahead and let our new guest here introduce himself.
Jason, thank you. My name's Ian Smiley. I'm a senior field application scientist with LI-COR in our support team.
Awesome, and I'm excited to have you on. This is our first go at a Teams recording, but I got to be honest, I was very tired of hearing from Jason and Rich and Doug, so I wanted to kind of mix it up.
It's a fair sentiment.
Maybe you can go into a little bit of what you do, where you're at, how long you've been at LI-COR, that sort of stuff.
Cool. Yeah. So I'm a senior field application scientist, but I've been with LI-COR for nearly 9 years now, and I sit in the support team in the European team, based in the UK, but generally provide technical support to customers across Europe. When I joined the company, I was originally part of the sales team and transitioned quite quickly towards support, because I come from a scientific and technical background. But more recently transitioned to the field scientist role, and now spend more time doing workshops, trainings, and things like that in the field and supporting our customers.
I kind of forgot that that's where you started. And how long have you been in this current role?
Oh, I moved to application scientist, I think, in 2019, and
good.
And field scientist in about 2 years ago.
Okay, so as long as I've known you, this is good. I didn't miss like a promotion or change in title. That's good. You have mentioned that you are out and about a lot, doing workshops, conferences, and things. Where have you been recently? Where have people maybe run into you?
So I'm recently back from the PEPG, the Plant Ecophysiology Group workshops in Portugal, and that was a really great experience. Seeing people working across a whole different range of sciences. Really fun event, and lots of interactions with both really new users and a lot of late night conversations with different professors over beers and arguing about the very fine details of ACI curves. But fun event, and really recommended to anyone that's considering attending that.
That is awesome. Where do you stand on ACI response curves?
We need to set them up well to look at the answer that we're trying to find and give ourselves the best opportunity to get that. And there's no right answer. There's just a million wrong ones. Or I believe the answer you were looking for maybe was it depends. But,
yes, I'm telling you, we need some t-shirts. So you have been a part of LI-COR for some time now, and I'm sure you were aware of the book. The book was in the works before I started at LI-COR, I believe. Did you have any particular role early on in the book?
So mostly just I've had a lot of discussions. I've reviewed a lot of the stuff as it was being written, mostly kind of sarcastic feedback and negative thoughts. But no, I think it's been really helpful. Certainly when I was doing my PhD, something like this would have been super helpful. And fairly early on, Jason and I were doing some workshops in France, and he mentioned this, and it's been really fun to read and look at that and see how it evolves, and also to remind Jason and Rich that occasionally there is a world outside of the United States, and some of the references and the in-jokes and things maybe need to be kind of tweaked a little bit so other people can actually understand them.
That's very fair. So there's a couple of things I want to touch on. I agree. I wish I had something like this as a graduate student or as an undergraduate student even. I think it's an excellent tool to really explain some of the inner workings and how we tend to think about things here at LI-COR. And to your second point, this kind of leads in well. Obviously, if you may notice, Ian and I don't exactly sound the same. There's a little bit of a language difference here. Before we embark on this episode, I think that we just want to be on the same page before we encounter any language barrier. So I just wanted to hear from us. So I also, for anyone listening, I show 0 notes to anyone who's joining the podcast. So they're quite brave, and I cower as I'm quite literally reading my show notes. But I wanted to hear from Ian in case something came up during this conversation. I'll provide some vocabulary words, and I would appreciate if you could give the UK equivalent for on the same page here. So
we'll go for the English dictionary, right?
Yeah, chips,
crisps.
Okay. You're a big fan of crisp varieties, is that right?
So this might have been slightly overblown, but that it was actually that trip a long time ago in France, where we covered many miles, kilometers even, across France in the back of in the back of our colleague Katya's small French car. Me, Jason, and Katya. And Katya, being the wonderful host that she is, cleaned out her car, made it all nice for us, and then Jason and I immediately dropped crisps all over the back seat, and it then became a quest to get as many different flavors of crisps as possible in this kind of 10-day road trip across France.
That is, I didn't know it was the same trip. I heard very small bits and pieces from that particular trip. I might have to ask more questions about that later. For
the listener, neither Jason and I nor I are particularly small people, and French hatchbacks tend to be very small cars. And for 3 people, a lot of luggage, a lot of LI-COR instrumentation, and a lot of crisps in that car was a good experience.
Not a good mix. Not really candidates to fit in a clown car. I don't visualize you nor Jason being particularly flexible, foldable. That would have been pretty great to see, actually. All right, so another one. Let's say I'm at an amusement park and I'm waiting in line.
You're queuing, I think you'll find.
So, okay. Line makes a ton of sense. It's the physical form of what people are doing. And also, queue, that's just a waste of vowels. It should be a letter. How are we queuing? It's like a verb of queuing.
I mean, I get that American English seems to be a kind of mission of getting rid of our vowels, but they, language can take on its own thing, right? It's it makes no sense to me. I have no idea.
I don't mind. I guess I don't mind Q. Line makes a lot of sense. I guess I'm on the fence about that one. I don't have. Okay, the next one I'm very curious about though. Okay, I don't know if this is actually true. We call them flashlights.
Torch.
Okay, you currently call them torches?
I currently call them torches.
You're aware of what century it is. Is this correct?
Yeah. It's, you should be aware of history when you have some.
Oh, that was good. I'm going to use that. You'll really rile some feathers here. Okay.
That was said with entire sincerity.
No, I love it. I think it's phenomenal. By the way, Ian, I told Doug that I was going to start this episode with our national anthem.
Okay.
But I don't think I was either going to do that or God Save the Queen. I don't know yet.
Mhm.
I
It's a bit late for her now, but
Okay, that one I'll cut out for your own sake. Um, okay, so last one, closet.
um, we'd use closet a lot, but I guess you're looking for wardrobe.
Yeah, is it still properly wardrobe over there?
Yeah, so
Okay.
wardrobe.
I happen to love that. I mean, like I read The Lion, the Witch, and the Wardrobe, and I just can't imagine The Lion, the Witch, in the Closet. Like, kind of takes
Seems
on
like
a
we have
different meaning.
different time
Um,
to that one.
yeah, different, a little bit different. But okay, so now we've kind of established this. Now we're on the same page here. So, um, now we know maybe who's right and wrong, but jumping into this chapter, and Ian, this is like a tough chapter. Previously, we've separated light from CO2 and water vapor. This is a tall order combining fluorescence and gas exchange, and so it's kind of intimidating. I do feel a little guilty, and we don't need to go into the complete nitty-gritty of every single aspect, but maybe let's just start off with, like, broadly speaking, what are the potential fates of light, and maybe that'll lead us into what fluorescence is.
Sure. I guess, certainly when we're doing trainings and things, the way I usually introduce it is, and it's always helpful if you can start with the Simpsons reference. But in chlorophyll fluorescence, our leaves follow the laws of thermodynamics, and the kind of key and important thing to remember with everything is that the energy that is absorbed from that photon of light, it has to go somewhere. It can't be created or destroyed. So we just have different paths that it can go to. And when we talk about fluorescence, we want our energy from a photon of light to be able to power the light-dependent reactions. But that's not the only place it can go to. I know there's been a bit of discussion in the past about how basically everything we make is a temperature sensor. A lot of that energy will end up dissipated as heat. We can also pass those photons and that energy into different systems, and it can be used for different fates. We can have the kind of formation of free radicals and high energy molecules, but these are dangerous molecules, and the plant desperately wants to avoid doing that. So the plant will induce non-photochemical quenching instead, and that provides a safe pathway to take that excess energy and again still to mostly lose it as heat.
Right.
But these are still not the only ways it can go. We can also get the re-emission of light from our leaf at a longer wavelength than what it was absorbed at, and we can split that into two sections effectively. We have long-term endemic emission of light, which is our phosphofluorescence, and then we get the very quick rapid turnover emission, which is our chlorophyll fluorescence, and we can measure it and we can quantify it.
So when you explain what fluorescence is like, it doesn't sound, that scary. It doesn't sound very intimidating, but I know you've talked to a lot of people. You bring up chlorophyll fluorescence and people quickly want to move on to something else. Why is that?
Yeah, I think at its core, we kind of feel like we have a good understanding of gas exchange. We get our base equations for water and CO2 converting to glucose. But fluorescence is this kind of slightly more ineffable thing, and it's really easy to measure. We can clamp onto a leaf and we can measure something in seconds. That measurement might not be very good, but it's possible. But the underlying relationships and the reactions in chlorophyll fluorescence, it's just a little bit more subtle. And I think with chlorophyll fluorescence, it's a really nice experiment that we can do. You can take your leaf, you can illuminate it with a blue light, put a blue filter on it, and you can see the fluorescence. Your leaf looks pink, and it's a really cool thing to do. But we don't usually see leaves under filtered blue light. We normally see them under sunlight or under our LEDs, and it's chlorophyll fluorescence is this kind of invisible thing that we're just slightly unaware of. Most of our customers, most of the people I talk to, they're biologists, and their training has mostly been in biology. And really, we're talking about phenomena that are based heavily in physics. Take a kind of good dose of chemistry, rate constants as well. But so it does pull people slightly outside of their comfort area.
Sure, and I agree. I was one of those people that was a little bit scared of fluorescence, not only of the concept, but
Me too.
being interested in fluorescence and potentially dipping your toe into this space. What are some of these key parameters that people should know and fixate on? We don't need to break down the math, but what are the most popular parameters for people to know?
If we go back to that core starting statement that energy can't be created or destroyed, it just has to go somewhere. And think about what our paths for that energy to go into. It starts to kind of allow us to think what is really happening here. So one of our core, most basic things we can do is think of a leaf that's in the darkness, and we apply a very, very small amount of light to it. Our measuring modulating beam is providing photons of light. It's providing energy that our leaf is absorbing, and it has to go somewhere. But if our leaf is in the darkness, then by definition it's not photosynthesizing, and we're not providing enough light for it to be able to photosynthesize. And if it's dark adapted well, and you'll notice there's a lot of ifs in everything I'm saying here, if it's dark adapted well, then the non-photochemical quenching pathway relaxes. So our leaf can't photosynthesize. There's no photochemical quenching or NPQ. You get some radiative decay, non-radiative decay, so dissipation is heat. But really, the only path that energy can be dissipated into is fluorescence. So that gives us our baseline fluorescence, our FO. Similarly, we can apply a strong pulse of light and overwhelm the photosynthetic machinery. But this pulse of light, this saturating flash, it's short, it's bright, so we close all of the reaction centers, but it doesn't last long enough to really induce photosynthesis. It doesn't last long enough to induce non-photochemical quenching. So again, we're manipulating the pathways that energy can be dissipated into.
Right.
So we can say some of our core parameters are our FM, the maximal fluorescence in the dark, or our FO, the baseline or operal fluorescence in the dark. And then the difference between them we call our variable fluorescence, or FV, which kind of comes to the really core main parameter that I think many of us see in general. That's our FV to FM ratio.
Right.
So that variable fluorescence divided by the maximal. And the reason it's so commonly used is because it gives us a theoretical maximum efficiency of our leaf. And it's really well conserved across higher plant species. So it's used so often because we know that maximum will be somewhere around 0.83 or 83%, give or take a little bit of noise for different filters and things. But we know that's the maximum efficiency. And if our plant is healthy and happy and dark adapted well, it should have an FV, FM of something around there, usually 0.8 or 80%, something like that. And typically, if it's significantly less than that, we can say either we messed up the dark adaptation or our plant is stressed, whatever that stress might be. It doesn't tell us why, how, anything. It's a fairly crude tool, but it is very sensitive.
Thank you for breaking that down very clearly.
Sorry, that was the long way around.
No, that's I think it's important to spend a little bit of time, because I think people read a definition and then they move on, and sometimes, I don't think it hurts to go a little bit more in depth. And you touched on something that is really cool. Everything you said was really cool. I don't mean to dissuade that, but the 0.82, 0.83, that highly conserved efficiency is really cool, because gas exchange is so variable and it's dependent on so many different things. Not that fluorescence is not, but it's such a highly conserved number that you really can compare apples to apples. I think increases its utility.
Absolutely. We just need to be careful of how we derive it. And the eternal question, probably the single question I get asked more than anything else, is just, how do I dark adapt my plant? When should I dark adapt it? And especially if you live in Northern Europe, where your days can be very long, people don't like the answer is, your best dark adaptation is to go out and make your measurement before dawn. And if you're up in Scotland and dawn is 4 a.m., then tough. But
that's a tough sale for a lot of people. That's pretty early.
Obviously, workarounds exist and people use clips or foil or whatever, but then that just gives us avenues for bias or things we need to be careful of as scientists to control.
Yeah, and we will get to that. We'll get right back to the podcast after a word from our sponsors. Oh, man. It's 4 a.m. The world is dark. The lab is colder than your advisor's feedback. And you, well, you've got to collect dark-adapted fluorescence data. Because apparently, this is the only dang time to collect it. But wait, don't drag yourself out of bed just yet. Introducing Sentod. That's right, Sentod, the overly confident undergrad who insisted he already knew how to operate the fluorometer. Let him march into the pre-dawn darkness armed with a headlamp, a clipboard, and completely unearned confidence. Guys, I don't know if I did something wrong. I think I accidentally calibrated the tripod. Guys. Oh, Todd. He's fine. He said he's done this before, probably in a dream. Meanwhile, you're at home, warm, asleep, and blissfully unaware that Todd's battling dew points and rogue sprinklers in your name. But don't you worry, by sunrise, you've got your data. Guys, it's dark. And Todd's got a valuable lesson in scientific humility. It's dark. I can't see very good. Send Todd, because no one with a graduate degree should be awoken before the chloroplasts Anyone have a flashlight? I'm hungry. Anyone? Something I want to touch just really briefly before that is the popularity of fluorescence, right? You've touched on a lot of the parameters, how we go about measuring some of these data, but it's so popular, people are still intimidated by it. Can you give a pitch of how you would convince someone to actually use this type of measurement? Like, what do you think it can tell those who are interested?
It's a cool question. It tells us about the energetic use and the efficiency that our plant is working at. Gas exchange might tell us the kind of net carbon gain, but it doesn't really tell you how it gets there. And one of the common examples is you could either have an absolute ton of Rubisco and have a high photosynthetic rate, or you can have less Rubisco and use it more efficiently. Chlorophyll fluorescence gets us to more, how efficiently are we using photons and where is that energy going?
Right.
And then from a measurement scheme as well, when we're working with light, we've obviously got something that can respond very, very quickly. We can control it very, very accurately. Whereas gases, you have to mix things and let things diffuse. And chlorophyll fluorescence becomes a quite simple measurement, but with a really complicated underlying science. It's like the exact opposite of gas exchange.
Yeah, that's great. I do kind of love that. So that's a really good pitch for folks who may be interested in kind of wandering into the fluorescence space. And if you would, I want to go back a little bit to this light versus dark adapted. And you mentioned there may be some grumpy people that are not morning folks. I'm a morning person. I am not a night owl, as some may say, but maybe kind of go into those differences between the light and dark adapted. You don't have to say which one's better necessarily, but which one is better. And don't say it depends. But
it very much does depend.
No, but what they are, how they vary, and how should we interpret them?
So, like I kind of touched on before, everything in the chlorophyll measurement is really about manipulating the pathways that we can dissipate energy into. And the really great thing about when we dark adapt is that we are closing off those pathways that compete for that energy that's being harvested in the light harvesting complex. So because those other pathways are closed, everything is going through the light harvesting complex, and we're really seeing that core efficiency. There's nothing else that's competing for that energy. It gives us a maximum efficiency. It's conserved, it gives us a baseline, and we can compare it. But plants don't exist as their maxima. They exist in a light environment. So when our plant, or when our leaf is in the light, it's photosynthesizing, it's dissipating energy through photochemistry, and it's probably also induced non-photochemical quenching as well. So all of these things are competing for that energy, and our efficiency will probably drop. We can still measure it in the same way. In the dark, it will be FO and FM. In the light, we measure our steady state fluorescence, so our FS, and our maximal fluorescence in the light, our FM prime. But we can still use the difference between those to give us an efficiency. People all over the world argue over what that term should be called, and that's probably one of the more challenging things in fluorescence, that there is not one, much like British and American English, there is not one consistent dictionary.
Agreed.
But for the sake of this, we'll call it 5PS2 because that's what LI-COR calls it in LI-COR's manuals, and it gives us that current efficiency that photosystem 2 is working at right now. Even in England at 4 p.m. in the afternoon, there's good light outside right now, and if I went out and measured my 5PS2, it will be considerably less than the FEFM because this is not a dark adapted leaf. So they're just different things. It's giving us our actual operating efficiency that the leaf is working at right now compared to some maximum efficiency, and both are useful. It depends.
No, you said it. No.
It is inevitable.
So there's those temporal differences, and then those interpretations. Obviously, what is happening in the here and now, and then what is this kind of theoretical, not theoretical, but the maximum efficiency. Well, how do we actually measure it, right? So like we apply light to the sample in a way that allows us to separate fluorescence from the light application and some from ambient illumination, but how do we measure it from like not a pure engineering point of view, but from an instrument point of view?
Yeah, so there are multiple different techniques for elucidating and measuring fluorescence, but when we talk about in the context of gas exchange measurements and the kind of measurements that are relevant to the book, what we're really talking about is panfluorometry, which stands for pulse amplitude modulation. Panfluorometry is this really cool technique that basically we can use what we call a modulating beam. So it's a beam of light that's turning on and off at a known and set regular interval. And because we're supplying an increasing amount of light to our leaf, it absorbs that energy and it has to go somewhere. It cannot be created or destroyed. So it elucidates a fluorescent signal. But because it has that modulating frequency and we know what that frequency is, the electronics of the fluorometer can separate the light from our modulating beam from the background light, or the what we would call the actinic light that's driving photosynthesis, or just the light in our chamber. And we can demodulate that signal purely to look at the amount of fluorescence that has been elucidated. At the same time, we can also apply, kind of touching these strong saturating pulses of light.
Right.
And that is supposed to be strong enough to overwhelm the photosynthetic apparatus, close the reaction centers, and really force the extra energy to be dissipated as fluorescence, because we've closed the other pathways for energy dissipation.
Mm-hmm.
So from an engineering point of view, we've got these two things going on simultaneously. Well, sometimes simultaneously, sometimes not, but we have a measuring beam that's modulating and flashing, and we have a flash that is creating that kind of overwhelming light intensity.
Right, and it's not long enough to drive the photochemistry, but it's there long enough to blind you. So don't look in it. I kid, it doesn't blind you, but I have seen polka dots for about an hour after I just stared right into it. Wouldn't recommend.
Pretty easy to do with the aquatic chamber for sure.
You know, I feel like one of those insects that is like flying towards the bug zapping light, and I can't help but not stare at it. But yeah. That's my own problem. So there is a really cool breakdown, kind of schematic of what this 6800 fluorometer chamber looks like. It's pretty cool in the book. I think people should check it out to really appreciate how awesome it is. And this is supposed to be instrument agnostic. The book, this podcast, this is in the title, the people that are doing it and all of that. But we are really proud of that chamber for lots of reasons. But one that I really want to obviously emphasize on this episode is because you can measure that fluorescence and gas exchange, in your words, simultaneously. Why is that so great? Why should people really value using that chamber and those data together?
Firstly, I just feel like I need to ask what the correct pronunciation of simultaneously is.
No, it sounds better when you say it. It sounds better when I say bottle of water. We don't need to go there, Ian.
Yeah. So when we think about really combining gas exchange and fluorescence, we're really looking at two different parts, and I forget which one, but one of the early episodes did I think a good job of setting the story of we don't measure photosynthesis. Photosynthesis has many processes. It's complex. There's lots of different parts to this thing, and they all come together to create a phenomena of photosynthesis. But when we look at chlorophyll fluorescence and gas exchange simultaneously, we're really looking at that net uptake of CO2 and that energetic supply. So there's really, really cool experiments that we can do. For example, if you look at how assimilation changes with light intensity, as the light goes up, assimilation goes up as you'd expect. But our chlorophyll fluorescence, if we measure it well and parameterize it well and don't just rely on the system defaults, we can also pull out our electron transport rate.
Right.
And if we plot electron transport rate versus assimilation, you get this linear response. And if you do this under low oxygen, then you get the kind of pure energetic requirement. So we see that it takes 4 electrons to fix 1 carbon molecule. And
that's mind-blowing to me still.
It's just incredible. It's one of the really fun things that we like to kind of talk about in workshops and stuff. This is just this is the fundamentals of where all of our food comes from, right? It's super cool.
We'll get right back to the podcast after a word from our sponsors. All right, science fans, listen up. You're measuring photosynthesis. You're calculating carbon fixation. You're going to love this. You're going to love my rates. Here's the deal. You've got your electron transport rate. You've got your carbon assimilation rate. You put them together, and bam! You've just unlocked the energetics of fixing 1 carbon molecule. You're basically turning photons into pure power, baby. Listen. Stop fumbling with theory and start slapping those rates together, okay? With electron transport versus assimilation, you'll know exactly how much energy it takes to lock down that 1 perfect CO2 molecule, tight, efficient, beautiful, baby. Electron transport rate. Get calculating, get caffeinating, get photosynthesizing. You're going to love these electrons. I guarantee it.
Exactly. Yeah, that's where, teaching plant physiology or just plant biology in general, it's like the underlying physics, biochemistry behind everything. It's remarkable what light, CO2, and of course water can do. Like, it's absolutely astounding. And so when you're measuring these together, you get a complete story. As LI-COR, we package these together with one chamber that's really pretty incredible. That control is important. Why should people really hone in on the environmental controls when considering using PAM fluorescence in the light and in conjunction with gas exchange?
So fundamentally, we're talking about something that's really sensitive, and we can influence it quite strongly, particularly when we're really thinking about how we go from our phi PS2, so our operating efficiency. If we multiply that by the light in the chamber, by the proportion of that light that's absorbed, and the ratio photosystem 2 to photosystem 1, then we can derive our electron transport rate. A lot of what we hope for as plant physiologists is that those electrons are being consumed in the light-dependent reactions and used to power photochemistry. But those are not the only electron sinks. And if we change the environment in our chamber, then we change the behavior of our leaf. One of the really, really big ones is temperature. Sure. If we're talking about C3 plants, Rubisco will start to fix oxygen at higher temperatures, and you're changing the photorespiratory rate of your leaf unless we really control the environment around our leaf. If the ambient CO2 in our chamber changes, again, you shift that ratio between photochemistry and photorespiration, and we start to see these things in our fluorescence data.
Yeah, and you can see it really quickly sometimes too, right?
Fluorescence responds almost immediately, and we really do need to be careful with how we control these things. And I think most of what we've talked about so far has been based on measuring in an enclosed chamber, but with other instruments and with the porometer, fluorometer, we measure in an open system. So so your leaf is open to the light, and if you change the light, then you change the fluorescence almost instantaneously. It's certainly faster than you can resolve in an instrument. So we really need to be really, really careful with how we treat the environment, that we don't shade our own leaves, or that we don't create bias in our own system.
Yeah, shading the leaves, yes, do not commit this offense. Which is, I believe the Madsen error is in one of the chapters. I'll have to maybe stitch in which one. It's somewhere in there.
There is a rather excellent cartoon of of the Madsen error. So
yeah, I hope to be famous someday, but not like that. This combination, this immediate control or lack thereof control, can drastically change someone's interpretations and of what this combined data should tell someone. So there's some great language here in the book that really goes into how fluorescence and gas exchange not only tells you what, but why, right? And so understanding how an improved cultivar shows significantly higher phi PS2 or lower NPQ during drought, and what that really means. Do you have any other particular examples that maybe are beyond the book that kind of showcase how these two together are very powerful?
Way back in my history, before I joined LI-COR, I did a lot of work in agricultural consultancy, and one of the things we were really interested in was how plants can get their roots down, and we were looking for deep rooting varieties to escape through drought stress. Unfortunately, at that point, the porometer fluorometer didn't exist, but being able to rapidly screen large numbers of varieties that are maintaining a stomatal conductance, using that to transpire, using that to keep the leaf temperature down, and possibly using that to kind of help aid a enhanced phi PS2 would have been a really wonderful opportunity had we had that back in the mid-noughties.
Are you jaded like I am, not having some of these cool toys when you were doing a lot of research?
My first experiences with gas exchange were using ergers from the 80s, and I was just so blown away that you could clamp onto something and measure something. I couldn't get over the idea that you could see photosynthesis, you could graph it, and then many years later I would have explained to me by Jason why that's not photosynthesis. But I think the tools have got better. I think quite often I still feel like a teenager seeing these things for the first time. It's still exciting.
100%. That's one of the largest draws of why I wanted to come come work at LI-COR was because of that kind of childlike wonder. I am childish, but a childlike wonder of some of these phenomena that we can now tease apart because of these incredible instruments that we make. I'm looking at the clock here. I've kept you for a while, and I was just hoping that I asked this of everyone that then kind of hops on. If you could maybe give a wrap-up statement here. What I like to pretend is if someone just fast-forwarded through all of our cool conversations and just wanted to hear the one takeaway message that is beyond read the chapter, but just one takeaway message that you would like to tell the listener, hopefully reader, of why they should, stay tuned to this episode and read the chapter.
I think as we've been going forward, I just keep going back and forward of like, I've spoken too detailed, and then also I've not spoken detailed enough, and that's maybe an inevitability, right? But no, what I would say is that I think chlorophyll fluorescence it's an incredibly powerful tool. It's really sensitive. It tells us a lot about how the leaf is working, but we need to be really careful with how we use it. We've touched on just a tiny little bit of the assumptions that go into making a chlorophyll fluorescence measurement. We haven't talked about choosing the intensity of your measuring beam, or the intensity of the flash, or the duration, or how there can be flashes of different shapes. It's a complex topic. It's really powerful, and we need to use it wisely. And hopefully the book gives some really good ways to think about how we can make sure that we're getting the best data possible, because anyone that's been listening to multiple episodes of this by this point must be really pretty focused on getting the best data they can. And
yeah,
it can tell you a lot. Don't just rely on system defaults. Think about what you're doing. Think about the processes that we're manipulating, and make sure that our measurement actually makes sense for what we're trying to get it to show.
Yeah, wise words. Thank you, Dr. Ian Smiley, for joining me here today for this episode. I appreciate you taking the time out of your day to talk with me and everyone here.
Thanks, Ian. It's a pleasure.
Thank you, everyone, for joining me here today. Don't forget to like and subscribe so you don't miss an episode. Trust me, you will not want to miss Dr. Lynch and I break down mesophyll conductance. But until then, stay curious, stay kind, and I'll talk to you soon.